Hi there. Hope you are all staying safe and healthy during the global health crisis. My name is Dan, and I am a PhD candidate at the University of California, Davis, and a researcher in the Laboratory for Embedded and Programmable Systems within the Electrical and Computer Engineering Department. In this presentation, I'll be discussing some of our recent work in non-invasive fetal oximetry. When a pregnant woman goes into labor, obstetricians monitor the fetal health using a technique called cardiotocography, which monitors the temporal relationships between the fetal heart rate and uterine contractions. In particular, a decelerating fetal heart rate after a uterine contraction may be a sign that the fetus isn't doing well and that a C-section to quickly remove the child from the offending environment is needed. However, research has shown that the addition of this technique has resulted in a five-fold increase in emergency C-sections with little to no improvements in fetal health outcomes. In the United States, currently 1 in 3 children are born via C-section, which is significantly higher than the World Health Organization's recommendation. As a major abdominal surgery, C-sections increase health risks to both mother and child and are associated with higher rates of chronic lung conditions, type 1 diabetes, and post-operative complications. Notably, a large portion of C-sections are performed primarily due to non-reassuring cardiotocography traces, where inter- and intra-observer variability is high. The problem with cardiotocography is that it has a high sensitivity to fetal hypoxia, but low specificity. In other words, there could be many reasons why the fetal heart rate may be dropping, one of which is fetal asphyxia, but not all of them necessitate the performance of an emergency C-section. A more objective metric of fetal well-being would be the fetal oxygen saturation, which is the percentage of oxygenated hemoglobin in the fetal blood. However, since the fetus is in the uterus, measuring this through typical means such as pulse oximetry is currently impossible, and there are no devices that can provide this measurement. To address this problem, we have been working on the development of a transabdominal fetal pulse oximetry system for the past several years to non-invasively measure the fetal oxygen saturation and provide physicians and worried mothers with this objective health metric. Briefly, pulse oximetry is a non-invasive technique to measure arterial oxygen saturation. Typically, it operates by sending a known light signal into the finger where it's modified by the tissue and captured by a detector on the other side of the finger. The changes in this signal is then analyzed to infer the contents of the tissue it traversed. For pulse ox, each heart contraction causes the arteries to expand slightly, causing a small dip in the measured light intensity. Since oxygenated and deoxygenated hemoglobin absorb light in the red and near-infrared regions differently, a ratio of this dip at both wavelengths can be used to estimate the relative amount of oxygen in the arteries. This technique has been around since the 1980s and has provided invaluable information about patient well-being to physicians in all fields. To perform transabdominal fetal pulse oximetry, or TFO, we utilize a reflectance-based optical probe placed on the mother's abdomen. Photons are introduced into the mother's tissue where it stochastically scatters and diffuses towards the fetus, of which some of them propagate back towards the skin surface and are captured at a detector. At this point, the signal is then measured, processed, and analyzed to extract the fetal signal and estimate the fetal oxygenation. While conventional pulse oximetry is relatively straightforward, performing TFO introduces unique challenges, one of which is the mixed signal problem. In order to reach the fetus, the light must first pass through the mother's abdominal wall and uterus. Therefore, any light that contains fetal information will also be tainted with an unknown amount of maternal information, which must be removed before calculating the fetal oxygen. Furthermore, natural variations in the fetal heart rates, fetal depths, and body sizes can cause a well-designed TFO system to fail if it does not account for the effects of patient variability. Designing a system that is robust to these types of changes is critical towards creating a clinically robust TFO system. In this paper, we propose that these issues can be addressed by incorporating additional context about the physical system into the fetal sensing approach. Broadly, the idea is that since the fetal signal is corrupted with an unknown amount of maternal signal, an externally measured signal of the maternal information could help provide some insight on how to attenuate its noise. In addition, spatial redundancy and knowledge about where the signals are being captured on the optical probe can help estimate the level of importance it has in providing fetal information. Lastly, the fetal signal estimates can be improved by utilizing historical knowledge about the fetal signal to predict and validate the quality of the fetal signal estimate. To accomplish this, a multi-detector optode that contains detectors at various source detector distances is used to capture redundant but spatially different information about the light tissue. Afterwards, external measures of the maternal heart rate and maternal respiration rate are used to generate a digital filter that attenuates the effects of the maternal signals relative to those contained in each of the detectors. Then, each of the filtered signals from the body sensor network are then combined through data fusion, where the signals that are from the detectors that are more sensitive to the fetal tissues are given higher importance, and the fetal signal is estimated by identifying a peak in the power spectrum in a typical fetal signal range. This estimate is then sent to the historical context module, where previous estimates of the fetal signal are used to predict the new estimate and provide a range of valid values for the current time point. In the case where the current fetal estimate is invalid, the prediction is used instead, which helps to improve the identification of the fetal signal over time. To evaluate this approach, we developed a TFO system prototype and utilized an at-term pregnant ewe animal model to capture measurements on an in utero fetus. Our TFO system prototype consists of a multi-detector body sensor network which houses the light detectors and emitters, the embedded optode control system to electronically control the actuation of the light sources and acquisition of the diffused light signal, and custom software running on the laptop to allow the user to select appropriate system parameters and provide visual feedback through real-time graphs on of the light intensity at each detector. To evaluate the context-aware fetal sensing approach, we utilized an at-term pregnant ewe animal model, where the fetal depth was controlled through surgical means. After placing an arterial line into the fetal carotid artery, a shallow fetal depth was created through an exteriorized fetal head from the uterus, but under the mother's abdominal wall. Whereas a deeper fetal depth was accomplished by returning the fetus fully back into the uterus. For completeness, the sheep were under full anesthesia and all of the procedures were approved by the UC Davis Institutional Animal Care and Use Committee, which is the animal equivalent of the governing IRB for humans. To highlight the proposed approach, I'll go through an example to show how the power spectral density changes at each stage of the proposed approach. We can see on the right that the raw light intensity measurements capture each of the detector channels, and the maternal signals, fetal signal, and associated harmonics are indicated with markers. As we can see, the fetal signal is currently hidden by the stronger maternal signals. After using an external measure of the maternal signals to filter the raw signals, we can see that a small peak at some of the channels become apparent, possibly indicating the fetal signal. All of the channels are then combined through data fusion to assign appropriate importance of the information contained in the signals from each channel with respect to its fetal information. We use a weighted sums approach where the weight of each channel is relatively assigned according to its source detector distance. The fetal signal is then estimated by finding the peak in the power spectrum and validated through the historical prediction model. To highlight the ability of this approach over time, several measurement datasets and their spectrograms are shown, and is compared to a naive approach of measuring the fetal signal. As you can see, the context-aware approach is able to correctly identify the fetal signal and is more accurate than the naive method. In addition, it's also more robust to masking the effects presented by the maternal signals, which makes the fetal signal estimate more accurate. In total, 5 10-minute measurements were evaluated on the pregnant sheep. Overall, the root mean squared error of the proposed approach was 3.65 times better than the naive approach and provides a lower overall worst case error in emergency scenarios. In this work, we presented some of our research in non-invasive fetal oximetry and proposed a context-aware approach to improve the accuracy of sensing in the fetal signal. Some of our future and current work involves the induction of various levels of fetal hypoxia while also capturing measurements on the TFO system, as well as investigating effects that labor dynamics can have on the quality of the measured signal. I'd like to acknowledge my colleagues from various colleges and departments with whom this work would not have been possible. And thanks to you for watching this presentation. Please feel free to reach out if you have any questions and hope that you have a wonderful day.